An exoplanet orbiting a star that entered our Milky Way from another galaxy has been detected by a European team of astronomers. The Jupiter-like planet is particularly unusual as it is orbiting a star nearing the end of its life and could be about to be engulfed by it, giving tantalizing clues about the fate of our own planetary system in the distant future.
This is the ESOcast, cutting-edge science and life behind the scenes of ESO, the European Southern Observatory, exploring the ultimate frontier with our host Dr. J, aka Dr. Joe Liske.
Hello and welcome to the ESOcast. In this episode, we're going to find out how an act of galactic cannibalism has brought a planet from another galaxy within astronomers' reach. Astronomers have detected nearly 500 planets orbiting stars in our cosmic neighborhood, but none outside our Milky Way has been confirmed. Now, however, a planet weighing at least 1.25 times as much as Jupiter has been discovered orbiting a star of extragalactic origin, even though the star now finds itself within our own galaxy. The star, which is known as HIP 13044, lies about 2,000 light-years from Earth and is part of the so-called Helmi stream. This stream of stars originally belonged to a dwarf galaxy, which was devoured by our Milky Way in an act of galactic cannibalism 6 to 9 billion years ago. Astronomers detected the planet by looking for tiny, telltale wobbles of the star, caused by the gravitational tug of an orbiting companion. For these precise observations, the team used a high-resolution spectrograph called FAROS, attached to the 2.2-meter telescope at ESO's La Silla Observatory in Chile. The planet, HIP 13044b, is also one of the few exoplanets known to have survived its host star massively growing in size after exhausting the hydrogen fuel supply in its core, i.e. the red giant phase of stellar evolution. HIP 13044b is near to its host star. At the closest point in its elliptical orbit, it is less than 1 stellar diameter from the surface of the star, or only about 0.055 times the Sun-Earth distance, and it completes an orbit in only about 16 days. The astronomers hypothesize that the planet's orbit might initially have been much larger, but that it moved inwards during the red giant phase. Any closer-in planets may not have been so lucky. Astronomers suggest that some inner planets may have been swallowed by the star during its red giant phase. Although the Jupiter-like exoplanet has escaped the fate of these inner planets so far, the star will expand again in the next stage of its evolution. When this happens, the star may engulf the planet, meaning it may be doomed after all. The astronomers are now searching for more planets around stars near the end of their lives. Their work may tell us about the distant fate of the planets in our own solar system, as the Sun is also expected to become a red giant in about 5 billion years. This is Dr. J, signing off for the ESOcast. Join me again next time for another cosmic adventure.
Today's telescopes study the sky across the electromagnetic spectrum. Each part of the spectrum tells us different things about the universe, giving us more pieces of the cosmic jigsaw puzzle. The most powerful telescopes on the ground and in space have joined forces over the last decade in a unique observing campaign known as GOODS, which reaches across the spectrum and deep back into cosmic time.
This is the ESOcast, cutting-edge science and life behind the scenes of ESO, the European Southern Observatory, exploring the ultimate frontier with our host, Dr. J, aka Dr. Joe Liske.
Hello and welcome to this very special multicast. We'll be exploring a unique collaboration between some of the world's most powerful telescopes, both on the ground and in space. Now, to do this, we've set up a similar collaboration between the ESOcast, the Hubblecast, the Spitzer Space Telescope's Hidden Universe, and the Chandra X-ray Observatory's Beautiful Universe.
I'm Megan Watsky for the Beautiful Universe from the Chandra X-ray Center.
And I'm Dr. Robert Hurt for the Hidden Universe from NASA's Spitzer Science Center.
It's the combination of deep observations from many different telescopes that makes this project so important. The longer a telescope spends looking at a target, the more sensitive the observations become, and the deeper we can look into space. But to get the full picture of what's happening in the universe, astronomers also need observations at a range of different wavelengths, requiring different telescopes. These are the key ideas behind the Great Observatory's Origins Deep Survey, or GOODS for short.
The GOODS project unites the world's most advanced observatories. These include ESO's Very Large Telescope, the NASA ESA Hubble Space Telescope, the Spitzer Space Telescope, the Chandra X-ray Observatory, and many more, each making extremely deep observations of the distant universe across the electromagnetic spectrum. By combining their powers and observing the same piece of sky, the GOODS observatories are giving us a unique view of the formation and evolution of galaxies across cosmic time, and mapping the history of the expansion of the universe.
Now, this is not the first time that telescopes have been used to give us extremely deep views of the cosmos. For example, the Hubble Deep Field is a very deep image of a small region of sky in the northern constellation of Ursa Major. This revealed thousands of distant galaxies, despite the fact that the whole field is actually only a tiny speck of sky, about the size of a grain of sand held at arm's length.
Now, with GOODS, many different observatories have brought their powers to bear on two larger targets, one centered on the original Hubble Deep Field in the northern sky, and one centered on a different deep target, the Chandra Deep Field South in the southern sky. The main GOODS fields are each 30 times larger than the Hubble Deep Field, and additional observations cover an area the size of the full moon.
These areas of the sky were already some of the most extensively explored, and so the combination of the existing archival data with the many new dedicated observations gives us an unprecedented view of the history of galaxies.
At ESO's Very Large Telescope on Serra Paranal, the 8.2-meter diameter giants were used for a total of almost 100 nights of dedicated observations. The telescopes made images of the region both in near-infrared light and on the boundary between visible light and ultraviolet light. At these short wavelengths, only telescopes on exceptional sites, such as the VLT's Serra Paranal, have a chance to observe through the Earth's atmosphere.
The NASA ESA Hubble Space Telescope observed the GOODS regions at optical and near-infrared wavelengths in order to detect distant star-forming galaxies, among other things. Now, Hubble spent a total of 5 days observing the fields, spread over 5 repeat visits. Each of these was separated from the previous one by about 45 days. Now, by spreading out the observations like this, Hubble was able to watch out for new supernovae appearing over the months, providing key information for studying the expansion and acceleration of the universe due to the mysterious dark energy.
But it wasn't just Hubble making space-based observations for GOODS. NASA's Spitzer Space Telescope imaged the GOODS regions in near and mid-infrared light for 5 days at wavelengths up to 30 times longer than the Hubble observations. These longer wavelengths are important for revealing distant galaxies whose light may be obscured by cosmic dust or stretched by the expansion of the universe, making them invisible to Hubble. For these distant galaxies, the Spitzer images also tell astronomers about their age and their total mass of stars, complementary information to the data from Hubble. Now, let's move from the infrared to much shorter wavelengths.
Also in orbit, the Chandra X-ray Observatory had already observed the GOODS field in many long observations taken over the course of a year. The Chandra images are the deepest X-ray images ever taken and detected more than 200 X-ray sources believed to be supermassive black holes in the centers of young galaxies. The X-rays are produced by extremely hot interstellar gases falling into the black holes.
These multi-wavelength observations identified tens of thousands of galaxies. To get a full understanding of the history and development of galaxies over the vast stretch of the universe's history, we need to be able to pin down their distances more precisely to fix them in cosmic time. As these galaxies are so far away, the light waves we see from them today started their journey up to about 13 billion years ago. And because the universe has been expanding since the Big Bang, back then the universe was less than 1/7 of its current size.
During the billions of years of the light's journey, its wavelength has been stretched as the fabric of space has expanded. This effect is known as redshift because, for example, light that was originally blue or ultraviolet in color is shifted to longer and redder wavelengths.
Back on the ground, astronomers used spectrographs on ESO's Very Large Telescope to capture the spectra of galaxies, spreading out their light like the colors of a rainbow. Now, the spectra allow astronomers to measure the redshifts of the galaxies and hence their distances. An extensive campaign produced redshifts for almost 3,000 galaxies in the GOODS fields. Now, with this knowledge, we can place the galaxies at their distances along a vast cone of space, stretching out from our own vantage point like a searchlight beam into the cosmos. We can take an amazing journey through kind of a tunnel towards the edge of the universe. In some places, the galaxies cluster together, forming structures which are up to tens of millions of light years in scale.
Thanks to GOODS and other surveys of the same region, these areas of the sky are uniquely well studied, with high-resolution, deep observations across a wide wavelength range. Plus, there's more to come. For example, the Atacama Pathfinder Experiment Telescope, or APEX, has spent a total of 300 hours, nearly 2 full weeks, imaging the region at submillimeter wavelengths from its high site on the 5,000-meter altitude plateau of Chajnantur in the Chilean Andes.
Observations at these wavelengths are ideal for finding the redshifted light of distant, dusty galaxies in the very early universe. Because of the longer wavelength of its submillimeter light, the apex image is not as sharp as the visible light and infrared images. However, thanks to the deep Spitzer images, as well as images made at radio wavelengths, we can match up and identify the objects found by apex with galaxies seen at other wavelengths. The submillimeter light glow reveals that hundreds of stars are being formed per year in these galaxies. In the next couple of years, ALMA, the Atacama Large Millimeter Submillimeter Array, currently under construction on the same plateau as APEX, will begin its first science observations. Also observing at submillimeter wavelengths, it will have much greater sensitivity than APEX, and resolution even better than Hubble. ALMA will revolutionize our understanding of the early universe, by revealing many more distant, dust-obscured galaxies that cannot be seen at all by visible light and infrared telescopes. These projects are an excellent example of how great observatories are joining together across the electromagnetic spectrum to give us a more complete view of galaxies over the history of the universe. Already, astronomers have written over 400 papers based on these data, with even more in the pipeline. And on top of that, the observations of the goods fields will continue in the future. These patches of the sky will be prime targets for the next generation of telescopes, both on the ground and in space. And astronomers around the world will use these data to learn new things about the universe for many years to come. Saying goodbye to our friends at the other observatories, this is Dr. J, signing off for the ESOcast and the Hubblecast.
This is Dr. Robert Hurt signing off for the Hidden Universe and the Spitzer Science Center, reminding you there's a hidden universe just waiting to be discovered.
And this is Megan Watsky, signing off for the Chandra X-ray Observatory and the beautiful universe.
Join me again next time for another cosmic adventure, which I'm sure will surprise us beyond our wildest imagination.
An international team of astronomers using ESO's Very Large Telescope has measured the distance to the most remote galaxy so far. This is the first time that astronomers have been able to confirm that they're observing a galaxy as it was in the era of reionization, when the first generation of brilliant stars was making the young universe transparent and ending the cosmic dark ages. This is the ESOcast, cutting-edge science and life behind the scenes of ESO, the European Southern Observatory, exploring the ultimate frontier with our host, Dr. J, aka Dr. Joe Liske.
Hello and welcome to the ESOcast. In this episode, we're going to find out how a team of astronomers used ESO's Very Large Telescope, the VLT, to confirm that a galaxy that had previously been spotted in images from the NASA ESA Hubble Space Telescope is in fact the most distant object that has ever been identified in the universe.
Studying these first galaxies is extremely difficult. They are very faint and small, and by the time their dim light gets to Earth, it falls mostly in the infrared part of the spectrum because it has been stretched by the expansion of the universe.
To make matters worse, at this very early time, less than 1 billion years after the Big Bang, the universe was not completely transparent. It was filled with hydrogen, which acted kind of like a fog and absorbed the ultraviolet radiation from the young galaxies. So, holding the record for having measured the redshift of the most distant object in the universe is not just a trophy to hang on the wall. It does have important astrophysical implications. This is the first time that we've managed to obtain spectroscopic observations of a galaxy from the era of reionization. In other words, from the time when the universe was still clearing out the hydrogen fog.
Despite the difficulties of finding these early galaxies, the new Wide-Field Camera 3 on the NASA ESA Hubble Space Telescope discovered several very good candidate objects earlier in 2010. They were thought to be galaxies shining in the early universe at redshifts greater than 8, but confirming the distances to such faint and remote objects is an enormous challenge and can only reliably be done using spectroscopy from very large ground-based telescopes.
The team was excited to find that if you combine the huge light-collecting power of the VLT with the sensitivity of its infrared spectroscopic instrument Symphony, and if you then use a very long exposure time, you just might be able to detect the faint glow from one of these very remote objects, and then go on to measure its distance.
A 16-hour exposure with the VLT and Symphony of the galaxy UDFY 381355539 did indeed show the very faint glow from hydrogen at a redshift of 8.6, which means that the light left the galaxy when the universe was only about 600 million years old. This is the most distant galaxy ever reliably confirmed.
One of the puzzling things about this discovery is that the ultraviolet radiation emitted by the galaxy doesn't actually seem to be strong enough to be able to clear out the hydrogen fog around the galaxy. So one possible explanation is that there must be other galaxies, probably fainter and less massive neighbors, that helped ionize the hydrogen in the region of space around the galaxy, thus making it transparent. Without this additional help, the brilliant light from the main galaxy would have been trapped in the surrounding hydrogen fog, and it could not have even started its 13 billion year journey towards Earth. Studying the era of reionization and the formation of the first galaxies is really pushing the capabilities of current telescopes and instruments to the limit. But this will be exactly the type of science that ESO's European Extremely Large Telescope will excel at. Once operational, this will be the largest optical and infrared telescope in the world. This is Dr. J signing off for the ESOcast. Join me again next time for another cosmic adventure.
Astronomers are observing the sky at ESO's Paranal Observatory in the Chilean Atacama Desert. In the course of the night, the telescopes on the mountain will collect around 125 gigabytes of data, enough to fill more than 25 DVDs. Until now, sending this huge amount of data back to ESO headquarters in Garching, Germany every day was a massive technical challenge. But a new fast link promises to make these difficulties a thing of the past. This is the ESOcast, cutting-edge science and life behind the scenes of ESO, the European Southern Observatory, exploring the ultimate frontier with our host Dr. J, aka Dr. Joe Liske.
Hello and welcome to another episode of the ESOcast. Today we're going to visit the barren landscape of the Chilean Atacama Desert. Here, an international consortium that includes ESO has recently finished installing a new high-speed data cable. This is part of a project to improve the communications link between the Paranal Observatory and ESO headquarters in Germany.
The project is called Enabling Virtual Access to Latin American Southern Observatories, or EVALSO for short. It is part funded by the European Commission's FP7 program. ESO headquarters in Garching a few weeks before EVALSO's completion. This site is 5 time zones and 11,500 kilometers away from Paranal. The night might be over for the astronomers in Chile, but work is in full swing here, with powerful servers downloading and archiving the new observations from the VLT. Because of limited bandwidth in the microwave connection between Paranal and the internet data backbone, it isn't always possible to get observations through straight away. Most of the time, VLT data arrives within a few minutes, but sometimes it takes hours. Delays of this magnitude aren't really a problem, but the operation of the recently commissioned VISTA, the Visible and Infrared Survey Telescope for Astronomy, poses much bigger challenges as it produces about 4 times as much data as the VLT every night.
In the past, the connection between the observatory and the outside world consisted of a microwave link, which was somewhat limited. Even after an upgrade in the spring, it was only able to transfer data at about the same rate as your broadband internet connection at home. Now remember, this had to serve a whole astronomical facility, with several world-class telescopes, as well as the usual internet and email traffic of the more than 100 staff that work there. So, this meant that bandwidth had to be rationed. In particular, the data from VISTA could not be sent through this link. Since the data rate from VISTA far exceeded the capability of the microwave link, the observations from this telescope had to be saved on hard disk first and then physically shipped back to Europe. A simple but somewhat impractical solution for a state-of-the-art observatory.
At the heart of Ivalso is 100 kilometers of newly laid data cable connecting the Chilean city of Antofagasta and 2 observatories, Paranal and Cerro Armazones. Armazones and its nearby peak currently host the observatory of the Ruhr University of Bochum, and if all goes to plan, the European Extremely Large Telescope, EELT, will be built on this mountaintop in the coming decade. In practical use, Ivalso is more than 100 times quicker than the old microwave link, and it can be upgraded to be faster still. With Ivalso, a whole DVD movie can be sent from Paranal to ESO headquarters in a matter of seconds. On the microwave link, that would have taken more than an hour. And this means that Ivalso doesn't just make ESO's work faster and easier, it opens up the possibility of new ways of working for the staff and users of the observatories.
And it all comes down to this. At the core of this cable is a bundle of plastic optical fibers. Now each of these is only about twice as thick as a human hair, and the whole thing is surrounded by padding and a tough skin. Now digital information is encoded as a series of extremely short flashes of light. These are sent down the fiber and decoded at the other end. It's the same tried and tested technology that underpins international phone and internet connections, and it allows tremendous amounts of data to be transferred very rapidly. So, although it's just an ordinary cable, it has the potential to trigger big changes at Paranal.
Ivalso will mean smoother and quicker operations for the VLT and a change of pace for the VISTA telescope. Staff in Europe will now be able to work remotely with their colleagues in Chile without having to make the long journey to Paranal, because video conferencing will be easier and smoother. In the case of sudden events like gamma ray bursts, which can only be observed for a few hours, this means that experts far away could be able to participate fully in the action, almost as if they were there. This is crucial since there isn't enough time to travel to the observatory before the gamma ray burst fades away.
For VISTA, the changes will be more fundamental. Soon, the data from this telescope will be sent back to Europe immediately for analysis. So instead of a long wait of up to 10 days while the hard disks are shipped to Germany, staff at ESO headquarters will have virtually instant access. With the work completed and the testing over, Ivalso is now coming into service. As a result, this remote mountaintop in Chile doesn't feel quite as remote anymore. This is Dr. J, signing off for the ESOcast. Join me again next time for another cosmic adventure.